Good morning to one and all. Today we are going to discuss our next concept here as Illumination Engineering here. And this one is a concept regarding the things of utilization of electrical energy subject. In this particular session, we'll direct to deal with the things of basic definitions and problems. Let's start our session. Yeah. Actually, what's this main thing of illumination engineering here is we'll deal with the things of light. I'd like to know what is meant by light is nothing but it's just a form of electromagnetic energy radiated from a body, and the human eye can receive it there. Yeah, and any heated body emits electromagnetic radiation. Let's understand one thing here. I would like to have some one body here, and I would like to heat this particular body up to the temperature levels of 500 degrees to 800 degrees C, and it becomes that particular body will becomes red hot. If I'd like to increase this temperature to the level of 2500 degrees to 3000 degrees centigrade, it becomes the red hot material will becomes the things into white hot. And it emits some sort of light there at this particular white hot region. That white hot region is also known as light. This one is the electromagnetic radiation. That electromagnetic radiation is both the parameters is there. It consists of heat as well as light. Yeah. And we all know that one more definition here. When I would like to pass some current, that having some resistance of R, it has some power loss of I square R. When I'd like to multiply with the help of some time, it has some energy. And it liberates energy in the form of heat. That one is a red hot. If I'd like to go beyond the things, it becomes some white hot or else light. And we have to understand one thing here. We are having some source. Let it be. We are having some source and we are having some effect. Let it be this one is a light. It liberates or emits light like this. That entire source that it is we are having some light is the cause. This one is a cause, and we have some effect here now. That effect maybe call it as illumination. Don't forget that one. Illumination is the effect, whereas light is the cause. And we have to remember one more thing here, that lambda stands for wavelength and f stands for frequency. These two are inversely related. Remember that thing. I may use it in the further things. When I would like to have some, if you are having some wavelength of this particular light is less than wavelength of heat, means it's inversely related now. Frequency of heat is less than the part of frequency of light. Remember this correlation. I may use it here. Yeah. The visible wavelength of light waves varying from 4000 to the part of 7500 angstroms there. 1 angstrom is nothing but 10 to the power of minus 10 millimeters. The eye discriminates different wavelengths in this range here, depends upon the sensation of color there. We all know that VGR, yeah, that it is violet, indigo, blue, green, yellow, orange, red. All these are some VGR colors. This range here is 4000 to 7500 angstroms there. And I'd like to plot one graph in between wavelength to the human eye sensation. This one visible region. And what's this 5500 is nothing but a sensation of human eye. It's a maximum peak point here now. This one is a human sensation eye visibility. And out of this particular thing, the middle one is nothing but greenish yellow. We can observe it. This one. And what's this one is nothing but VBR. And radiations, when I would like to go for the part of short length wave radiations here, that it is not in the visible region, that we can consider it as X-rays. We may use these radiations for the part of it can penetrate through our bodies. We can use it in X-rays there. What's the thing? Having some wavelength low. And obviously when the wavelength is low, frequency is higher. Remember that. Yeah. Light is nothing but it's just an radiant energy from a hot body that produces visual sensation upon the part of human eye. It is represented with the letter Q. Luminous flux is represented with the letter F, or else we can use some phi like this. It's nothing but it's just an energy in the form of light waves radiated per second. We may call it as luminous flux. It is represented with the symbol F or else phi. And unit for this luminous flux here is lumens. Don't forget that one. Yeah, observe this particular one. We can have some light like this. I can have some electrical power input. It emits some radiant flux like this. Yeah, that maybe call it as this one is the output. And what's the input here? This one is the input. Efficiency is nothing but we all know that efficiency is nothing but output divided by input. Yeah, and what's that? I already discussed when current passes through a conductor, some heat is liberated. That loss may be called as I square R, which increases its temperature. It becomes red hot material, and then it becomes white hot. In the first slide, we discussed this one, and finally, it has some light. Yeah, we can observe that particular light there. What's that? Radiant efficiency is nothing but energy radiator in the form of light divided by total energy radiated by the body. Maybe call it as efficiency. Output divided by input. Yeah. And the next definition part here is what is meant by plane angle. Plane angle is nothing but when I would like to have some two convergent lines like this. It has some arc maybe like this. Yeah. And they can create some sort of angle that it may be called as theta. The angle subtended by at a point in a plane by two convergent lines may be called it as theta or else plane angle. Its arc length divided by radius will use this particular angle. Same definition. If I'd like to go for the part of solid angle, just replacing this particular thing with the help of some area that may be called it as solid angle, and it is represented as omega like this. Solid angle is the angle subtended at a place at a point of space by an area. Don't forget area. That it is omega. Area divided by square of the radius will give the information of omega there. Previously, arc length divided by radius. It's an area there. Don't forget. We have to consider area wise. The solid angle subtended at an sphere here is area of the sphere divided by radius square. If I'd like to choose some area of the sphere here is 4 pi square divided by r square. These two r square cancel. What's this angle? 4 pi. We may call it as ordinary, we can call it as radians. But while going for the part of some area wise, steradians like this. The unit for the part of solid angle, steradians is the unit. And if you previously we are having some arc length divided by radius now. If I'd like to choose only radius, we can't get this value of 4 pi. That's why you can consider radius square. This square and square cancel out, we get the term of 4 pi steradians. And the next one, luminous intensity there. It is represented with the letter I. Just remember how much flux enclated upon the part of solid angle will give us the part of which thing luminous intensity. And the unit for the part of this one is lumens per steradian, or else we can have some other unit, candela. Both the units are valid. That's not an issue. Flux per solid angle will give us the information of luminous intensity. Or from the same thing, can we elaborate the things of phi? Yeah, simple thing. I into omega is also valid. Or else, can you elaborate the part of omega is equal to what's this thing? Phi by I. I is the representation of luminous intensity. Lumen is nothing but it's just a unit of which thing here, luminous flux. And previous slide, phi is equal to, we can have some formula. Phi is equal to candle power into omega. Total flux emitted by a source of 1 candle power is how much angle here? 4 pi lumens. Yeah, candle power is equal to lumen by solid angle. And finally, we can have something. Illumination is defined as luminous flux received by the surface area. Luminous flux received by the surface area will give information of which formula? E. E is equal to illumination. Don't forget this formula. It's a frequent formula. I use it here. E is nothing but illumination or else effect. E is equal to flux per unit area. And units are lumens per meter square. Next one, brightness. It is represented with the letter L. Luminous intensity to the part of angle of A cos theta will gives information of brightness. Just it's a formula. Yeah, observe this particular slide, measurement of light here. This one is a candle. The surrounding rays may be called it as luminous flux. Intensity is nothing but we'd like to consider upon the part of this particular solid angle. Illuminance is nothing but lumen per meter square, or else we call it as flux per area. Will give the information of which thing? Illuminance. Luminescence is nothing but candela per meter square. Yeah, don't forget this is a candela per meter square, whereas this one is flux per area. Another definitions wise, mean horizontal candle power (MHCP) is defined as mean of the candle power in all the directions. In all the directions we can consider. In the which plane here? Horizontal plane. If I'd like to consider MSCP is nothing but mean spherical candle power. Mean of candle power of in all the directions on all planes there. We may call it as MSCP. It's a frequent formula, is it? MSCP is equal to, we can have some flux by 4 pi is the formula, or else may write it F by 4 pi is also valid. Means spherical candle power. Hemispherical in the sense only half of the planes, whether it's an upper half or lower half. Hemisphere. Whereas this one is spherical now around surrounding things, every direction. Reduction factor is nothing but it's just a ratio of MSCP divided by MHPP. SH reduction, SH, S by H. That's the remaining things are common. CP. MSCP divided by MHCP. Lamp efficiency, we all know that lamp efficiency is nothing but, let it be we are having some lamp. I can project like this. We can have some light here. That light is nothing but flux. And what's this input of this particular lamp here is power. This one is the output and this one is the input. And what's the efficiency there? Luminous flux divided by power input is the lamp efficiency. That's the only simple definition was. Next definition, utilization factor. Utilization is nothing but, let it be I would like to on one light. It can ventilate like this in this entire room. Yeah, total lumens reaching the working plane. This one is working plane divided by total lumens emitting from the source. This one is a working plane. That factor may be called it as utilization factor. How efficiently you can use all the lumens, that may be called it as utilization factor. It is obviously less than 1. Maintenance factor, it's nothing but illumination under normal working condition divided by illumination under everything is clean. Maintenance factor. If you are having some specific room, if this room is entirely clean and the maintenance factor is obviously 1. Depreciation factor, it's a reciprocal of maintenance factor there. Reflection factor or coefficient of reflection. The incident ray like this, it has some reflected ray like this. When I would like to draw some normal like this perpendicular, that gives the information of incident, reflected and the normal rays. This normal is with respect to which thing, how much angle right now? 90 degrees. All these are some basic definitions. We may use it in the numerical section there. Yeah. Let's start our numericals part. It's a simple numericals if you can understand. The flux emitted by a lamp in all directions is 1000 lumens. Yeah. We are having some specific lamp maybe like this. It can emit some lumens there. How much lumens here? Phi is equal to 1000 lumens, or else we can write it as F. That's not an issue. Calculated mean spherical candle power. MSCP stands for mean spherical candle power. You all know that formula. Flux divided by 4 pi will give the information of mean spherical candle power of the lamp. F or phi is equal to 1000 divided by 4 pi. It's approximately 80. That's it. Simple. Another one. Just observe this question. A 250 volts lamp has a total flux of how much? 3000 lumens and takes a current of 0.8 amperes. Calculate lumens per watt, MSCP per watt. That's it. Yeah. Observe. Current is nothing but how much value they have given? 0.8. Voltage, they have given some 250. Wattage is nothing but power is equal to what's the formula? V into I. Just multiply that one. That may be called it as wattage of the lamp. 250 into 0.8 will give some wattage. 200 watts is the total flux. F or phi is equal to 3000 they have given. MSCP, we all know that flux by 4 pi will give us information of mean spherical candle power formula. 3000 upon 4 pi will give us information of MSCP value. In a similar words of fast bit, lumens per watt, that it is lumens per watt is nothing but output of the lamp here is 3000 lumens, and what's the input here? Wattage. Yeah, for the part of this lamp, when I would like to glow like this, we can have some input and we can expect some output is flux. Phi divided by input, that it is wattage. How much wattage here right now? 200. 3000 by 200, it's approximately 15. It's a ratio. MSCP per watt, I already remembered MSCP value is 240. Divided by wattage here is 200. It's approximately 1.2 is the value. Just simple numerical wise. In order to find out wattage, power is nothing but V into I. Remaining everything is common. Yeah. Observe one more thing. Determine the MSCP of a lamp emitting 1000 lumens. It's obviously they have given 5. Inclined plane of 60 degrees to the rays is kept away 5 meters. It's just an angle away from a 100 candle per lamp. Find the average intensity of the illumination of the surface. Yeah, it's a simple thing. I can remember some laws of illumination here. Illumination E is equal to, we can have some I by d square is the first law. Coming to the part of angle wise, cos theta, Lambert's cosine law. I may use this Lambert's cosine law. Yeah. MSCP of a lamp here is, I know the formula, F upon 4 pi. 1000 divided by 4 pi will give the information of which thing? MSCP. I am going for the part of average intensity of illumination. Remember, illumination is represented with the letter E, effect E. I divided by d square into cos theta. Yeah, from the source, having some candle power of how much? 100 candle power. We'll have some rays like this at an inclined plane of distance of how much here? 5 meters. How much angle it creates here? 60 degrees. But they pose some question like this. So the rays is kept away 5 meters away from the candle power. It's an angle I would like to find out this one here. Just observe, I would like to find out this angle. This total angle is how much? 90. But they have given 60 degrees. What's this remaining angle here? 30. That 30 is the value. This one is the just substitute theta is equal to 30 degrees. Don't go for 60 degrees. Why means with reference to the source I would like to consider. I divided by d square into cos theta. The theta here is 90 minus 60 will give us information of 30 degrees like this. And unit for the part of illumination 3.46 flux. In a similar thing, we can observe it's a simple numerical. That's not an issue. Don't forget the formula. Illumination is equal to phi by area. Phi stands for flux area. Yeah. This one is a typical numerical. Just pay attention here in order to finalize the things of this particular numerical. The illumination of this particular office is they have given some 30 into 10 meters length, that it is area wise, is to have a value of 220 lux and is to be provided by a number of 200 filament lamps here. They have given some two factors. Utilization factor is 0.3 and the maintenance factor here is 0.8. Calculate the number of lamps required. The efficiency of each lamp is 12 lumens per watt. Okay. Actually, they have given one room here like this. And they have given, let it be this room will have some dust or anything else. At the time, we have some utilization factors, how much here? 0.3. And the maintenance factor here is 0.8. If there is any dust or anything else shaded part like this. My question is, if you are having some room like this, it is clean there, everything is clean. At the time, what these two factors will becomes? It's obviously 1. For the specific room, in order to have the center lighting wise, we can require some, let it be 100 lamps like this. When the room is clean, we can't require that much of lamps. That lamps that reduce there. Let it be only 50 lamps is enough if the room is clean. If this entire room is somewhat shaded, dust, everything is there. At the time, we required so many lamps there in order to operate this particular room. Whereas in this one, it's a clean. That's why there is some reduction in the lamps. We have to find out how many lamps are required at this particular utilization factor and maintenance factor. Whereas in this one, it's a clean now. It's a reduction is there. Just I want to proceed like this. Area of the room is the first thing, 30 by 10. It's approximately 300 meters square. Illumination required, we all know the formula. E is equal to what's the formula? Flux per area. From that, what's that lumens phi is equal to E into A. What's that E is nothing but illumination required, they have given some 220 lux. What's that A is nothing but 300. 220 into 300, it gives some 6600 lumens is a part of the specific room. Yeah, just only one formula. That's enough. Yeah, they have given some utilization factor of 0.3 and the maintenance factor of 0.8. Just observe total lumens required from the source. Just remember, if they have given any factors like this, if those factors are less than 1, keep it all those things in the denominator part. Yeah, that it is A into E is nothing but illumination divided by factors. Yeah, A into E. Already we calculate that particular one. A into E is 6600 divided by factors there. Yeah, it's not on depreciation, it's on a maintenance factor. We can have some values maybe like this 6600 divided by 0.3 into 0.8. We'll use that total lumens here as 2,75,000 lumens. When these factors are considered, if the factors are less than 1, keep it in the denominator. That illumination, that entire thing of A into E, flux that it is lumens divided by utilization factor into maintenance factor, will use the total lumens required from the source. And the total voltage required here is total lumens required by lamp efficiency. How we get this factor here is, can you remember efficiency formula? That it is flux divided by wattage. From that, can you find out the things of this particular wattage W? Flux divided by efficiency. That's the only formula we use it. Yeah. What's that efficiency is nothing but we are having some light. It liberates its like this flux output. Input here is power. 5 by power. This one wattage. We get that one. W is equal to 5 by efficiency, lamp efficiency. Total lumens required from the source here is 2,75,000 divided by lamp efficiency. They have given some 12. 22,916 is the total wattage. And when I know this total wattage, number of lamps required here is total wattage divided by wattage of each lamp. For the wattage of each lamp, they have given some 200. Use that one. Total wattage we identified like this 22,916. We get that how many lamps you have to use it for the part of in the specific room here is 114 lamps required. That's the only thing. 114 lamps are required. Just observe one more thing. If the room is clean, what about this particular factor here? Only 6600 lumens is enough. And there is no depreciation factor, maintenance factor, everything is becomes 1. At that time, the number of lamps required here is, it's obviously there is some reduction. Why means, and when the room is not clean, we can require 114 lamps. When the room is not at all clean, when the room is somewhat clean, everything is possible, we require obviously less than 114 lamps. That one is also one more thing. Yeah, it's a typical numerical if you can understand. Yeah. Thank you one and all for watching my class there. If you like it, please subscribe to my channel. This one is our channel. Thank you.